Welcome to CEDA-Labz. Module 4, Programmable Devices. We will be studying FPGA. Let's start with the basics of FPGA. The first question arises in mind, why we need FPGA? Or why we need programmable gate array? As discussed in the previous modules, first programmable device were SPLD, after that CPLD, and then PGA. As complexity increased, so gate count for implementing desired logic also increased. Available devices like SPLD and CPLD are not best fitted for this logic. Due to this reason, industry developed programmable gate array. When complexity increases, then number of gates required for implementing the logic also gets increased exponentially, as available hardware SPLD and CPLD have limited number of gates. Also, in these designed hardware structure, there's limited flexibility of changing hardware according to our desired logic. And that was not even guaranteed. In simple words, we can say that upgradation in these available structures were not possible. It would lead to a completely new system. No doubt that programmable gate array device is the extension of SPLDs like EPROM, PEL and CPLD. Both EPROM and PLDs can be programmed in batches in a factory or in the field. Basically, there are two types of programmable gate arrays. MPGA means masked programmable gate array. EPGA means field programmable gate array. First, little bit of discussion about masked programmable gate array. MPGA is a type of programmable gate array which is customized during fabrication, means their connections are fixed permanently during manufacturing and can be changed again according to our needs. It means that we can implement only one logic particularly in this type of programmable gate array. This type of designing takes more time and higher risk, as its connections are fixed compared to FPGA where connections are reconfigurable. So, speed of MPGA is always high as compared to FPGA. In terms of logic density of MPGA is always high compared to FPGA because MPGA does not contain any unwanted gate. Now coming to FPGA, first question arises in mind, what is FPGA? EPPGA is field programmable gate array. Second question arises in mind, what is field? Why F? Most of the people think that here field means something related to electric field or magnetic field. Is it so? Guess what? So, field. In field gate array means field user or end user who is using this programmable gate array for implementing its desired logic. So, F is used with PGA, and this FPGA comes in the picture. In the early 80s, during the era of VLSI, in order to make connection between different ICs for developing systems, need of glue logic arises. The glue logic is a type of logic circuitry, which is used to interface a number of integrated circuits together. But due to this, new problem aroused. Number of glue logic in a system increased, and due to which, area of system increased. It was noted that systems had a few VLSI components, and lots of MSI and SSI components as glue logic. In order to minimize the glue logic, custom ICs were designed. But this approach was best suited to the products, which have very high volume. So, in mid-80s, around 1985, field programmable gate array, that is, EPPGA, was introduced in place of custom IC for implementing glue logic. Xilinx is the first company who developed FPGA in mid-80s. Basically, field programmable gate array FPGA is a type of ASIC. As discussed in previous module, we saw that FPGA is a type of semi-custom ASIC which is programmable. This figure shows the ASIC classification. As we can see, FPGA comes under programmable ASIC. FPGA was first developed by Xilinx in the year 1985. Basically, gate count in FPGA is much high as compared to CPLD. So, those designs, which are not going to fit in CPLD criteria, FPGA are preferred there. Field programmable gate array is a type of integrated circuit, which can be configured by the end user according to their need. Any digital circuit will be implemented in a FPGA. EPROM is a type of programmable IC. EPROM is a type of ASIC, but it is different from normal ASIC. In traditional ASIC, the function is specified during manufacturing, but in FPGA function is specified by the user after the manufacturing. Basically, it is programmed by users to implement circuit at their workplace. Also, programming time of FPGA is very fast, sometimes few seconds or minutes as compared to traditional ASIC. Now coming towards advantages of FPGA. First advantage of FPGA is that it is reprogrammable. We can reprogram it again and again according to our needs several times. Second advantage of FPGA is that it has low non-recurring engineering, that is, NRE cost, compared to other traditional ASICs. NRE cost refers to one-time cost to develop a new product. They are good for prototyping. There is a small time for implementing any logic in FPGA. It also acts as testing device for different digital circuits. They are economical for product protection. FPGAs have large amount of scope. They can be used at many places: home appliances, in communication systems, in control system and automation, mechanical and civil engineering, in testing, in medical electronics, in aerospace application, in academics, so we can see FPGAs are useful in many applications. Based on the programming technology, the FPGAs can be divided into three types: anti-fuse FPGA, flash FPGA, SRAM FPGA. First, let's discuss anti-fuse technology FPGA. In anti-fuse technology, there are some set of fuses. An FPGA device is configured by burning a set of fuse. An anti-fuse is fabricated as a normally open disconnection, and connection in the technology is established by burning the fuses. Once the FPGA is configured, it cannot be reprogrammed again. So, basically it is a one-time programmable technology. In other words, we can say that all the FPGA which uses anti-fuse technology are programmed only one time and cannot be reprogrammed. All of this logic cells are made from conventional logic gates. For small volume production, in place of ASIC, this technology is preferred. All the anti-fuse programming elements share common properties. Basically, anti-fuse is an electrical device that performs opposite function to a fuse. A fuse starts with a low resistance and is designed to permanently break an electrically conductive path, whereas an anti-fuse starts with a high resistance or high impedance and is fused into low impedance state by applying high voltage. When a programming voltage is applied across the anti-fuse, it makes a connection between the metal line above it and to the metal line below it. The anti-fuse technology is very low on resistance. Size of anti-fuse are very small, due to which interconnects occupy less area. The next programming technology is flash technology. The FPGA device, which is using flash technology, can be reprogrammed several times and are non-volatile in nature. It can be programmed by field user. Reconfiguration time for this type of FPGA is few seconds to few minutes. The ultraviolet rays are used for reprogramming the flash FPGA chips. Flash FPGA is also known as EPROM or EEPROM programming technology. In the EEPROM programming technology, each cell looks like a MOSFET as shown in the diagram. In the cell, on top, there is a controlling gate. Also there is a presence of floating gate, FG, insulated all around by an oxide layer. The floating gate will be present between control gate and MOSFET channel. As floating gate is electrically isolated by its insulating layer, electrons placed on it are trapped under and until they are removed by the application of electric field. Basically there are two gates, floating and select. In order to make channel conductive, high voltage must be applied to control gate. Once the floating gate is charged, the electrons in it cancel the electric field from control gate. Basically, an EEPROM flash programming technology cell will be present in two modes. Normal where there is no charge on floating gate and cell is normal N-channels transistors, and second is charged mode where floating gate is charged by applying high voltage and transistor is turned off permanently. In EEPROM programming technology, no external device is required for storing the information. Also, EEPROM FPGA is reconfigurable, but in this technology reprogramming is a time-taking step. UV light is used for reprogramming the FPGA. Electrically erasable programmable read-only memory technology, that is, EEPROM. There is a slight difference between EEPROM and EEPROM technology. In this EEPROM technology, we use electricity for removing the data instead of ultraviolet rays. EEPROM's working is same like EEPROM technology. It also has two gates, floating and select. Its structure is different from EEPROM cell. In standby mode, its threshold voltage is negative. The main advantage of EEPROM technology is that it consumes less time as compared to EEPROM technology. So it saves a lot of programming time. More number of voltage sources is required in this technology. The disadvantage of this technology is that area required is more as compared to EEPROM technology. The requirement of area is almost twice. Now we will discuss our next technology, that is, static RAM technology. Static RAM FPGA, or we can say SRAM-based FPGA. This is the most widely used FPGA technology all over the world. In this type of FPGA, there is an unlimited programming, that is, FPGA can be reprogrammed again and again. This is the main advantage of this technology. In this type of FPGA, some additional circuitry is required for loading the program into an FPGA. In this technology, reconfiguration is very fast, which saves a lot of time. The basic cell in the SRAM technology is SRAM. Then, what is SRAM? An SRAM is made of a 6 MOSFET. Each bit in an SRAM is stored on 4 transistors, M1, M2, M3 and M4, which form 2 cross-coupled inverters, as shown in the figure. This SRAM storage cell has 2 stable states, which are used to store the states 0 and 1. In the diagram there are 2 extra transistors, M5 and M6 present, which are used to control the read and write operation. In addition to 6T transistor SRAM, 4T transistor SRAM is also popular. The SRAM cell works in 3 modes: standby, reading, writing. So this SRAM cell controls the configuration of logic block during programming. SRAM-based FPGA are volatile in nature. They lose all configurations after power off. So, there is a need of external storage device during configuration. EPROM is used for this purpose. So, FPGA in this technology is reprogrammable again and again. Static RAM FPGA requires very less, or we can say very small time for configuration, since each SRAM cell contain either 6 or 4 transistors. As there is lots of SRAM cells present inside an FPGA, so FPGA, which are based on SRAM technology, required large area. Since SRAM-based FPGA is volatile in nature, they need power all the time for storing the configuration data. As we discussed all types of technology, which is required for FPGA design, lastly we'll compare all these technologies. The first feature for comparison is reprogrammability. SRAM-based FPGA are reprogrammed again and again, whereas anti-fuse technology-based FPGA are only one-time programmable, and flash-based FPGA are also reprogrammable. Second feature is reprogramming speed in all the 3 technologies. SRAM-based FPGA have fast configuration speed compared to other 2 technologies. Third feature is volatile nature. Out of these 3 technology, SRAM-based FPGA are volatile in nature, whereas anti-fuse and flash-based FPGA are non-volatile in nature. Fourth feature is size. SRAM cell have large size compared to anti-fuse and flash technology. Thus, SRAM-based FPGA consumes more area. Power consumption in anti-fuse-based FPGA is less compared to SRAM and flash-based FPGA. In this tutorial, we discussed basics of FPGA. Initially, we studied about PGAs and why they were needed. Then, we studied its types, MPGA and FPGA. And, then, we went into the detail of FPGA. Further, we got to know its advantages and its scope. Moving on further, we studied types of FPGA. And then, we compared these different technologies under various aspects.